Hey everyone, continuing on some messier L'Hopital's rule examples. I have a nice one here where if we can work our way through, as n gets really big, this is going to approach 0. So in the parentheses, I basically have 1. So this is like a 1 to a really big power. But it's not quite 1, it's something a little tiny bit bigger than 1. So is the fact that 1 to a power is generally just 1 going to win? Or is the fact that something bigger than 1 to a really big power tends to get really big? And this is another one of those indeterminate forms that's not L'Hopital rule ready. So we're going to have to do a little bit of, it's actually like total side work here. We're going to say, I don't actually know, but whenever I have something exponential, I can try throwing in a natural log. And sometimes that allows me to rewrite as a fraction, and then I can use L'Hopital's rule. So I'm going to go ahead and bring that n out of the exponent. So I have n times the natural log of 1 plus 1 over n. And now, as n gets really big, I'm getting infinity out in front, and then the 1 over n is approaching 0, which means that second factor is getting close to the natural log of 1, which is 0. So now I have one that's very nicely suited for rewriting as a fraction by dividing by the reciprocal. So we're going to say, still on our kind of tangent here, sidetrack, limit as n approaches infinity of the natural log of 1 plus 1 over n divided by 1 over n. So dividing by 1 over n is the same as multiplying by n. And now when I look, we know the top is approaching 0 and the bottom is now also approaching 0. So I can apply a L'Hopital's rule finally. L'Hopital's rule says take the derivative of the top, which is going to be a 1 over 1 plus 1 over n. Natural log stuff, the derivative is going to be 1 over stuff, and then times the derivative of stuff. The derivative of 1 is 0. The derivative of 1 over n is negative 1 over n squared. Remember, 1 over n is n to the minus 1. And then on the bottom, I get that same thing, negative 1 over n squared. And then I would just straight up cancel those out. That works out really nicely. So notice if you forget your chain rule, you're going to really be messed up on this. Now, if I look at the limit as n goes to infinity of 1 over 1 plus 1 over n, the 1 over n goes to 0, and it looks like I'm getting 1 over 1, which is 1. Okay, so this is great, but what I really found out is that the limit, well, I'm not even going to write the limit in. The 1 plus 1 over n to the n, the natural log, that's what I was going for, is approaching 1. But the question is, what does it do without the natural log? And the answer is, to get rid of a natural log, you exponentiate with a base e. So we're going to get e to the 1, which is just e. And this is one of those, you see e in pre-calc, probably without a lot of explanation of why it's so cool. Here's where it comes from, one of the why it's so cool things. E comes out from taking this 1 plus 1 over n to the n and letting n get infinitely large. It comes from that tug of war between 1 and infinity. What happens when 1 and infinity battle? We end up with e. Okay, so natural logs if you have exponents involved. D, I think D might just be messy. I don't see anything too weird where we're going to have to rewrite. But I do see if I plug in 1, I get 1 minus 1 plus 0. Natural log of 1 is 0, which is 0. And then on the bottom, I get 1 and then cosine of pi. So I'm over on the far left, which means my x is negative 1. So I get 1 minus 1. So it is a 0 over 0. And I'm going to apply L'Hopital's rule. Okay, so on the top, derivative of 1 is 0. The derivative of minus y is minus 1. The derivative of natural log y is 1 over y. And then on the bottom, oh, what am I doing? Derivative of 1 is 0. Derivative of cosine is minus sine pi y. And then I need to chain out a pi. And, do I need to? I don't even think I need to. Oh, maybe I do. If I let y go to 1 now, I have negative 1 plus 1, which is 0. And then on the bottom, sine of pi is 0. So 0 over 0 still. And I think I will try clearing the fractions in fractions. So I'm going to go ahead and multiply by y over y. So this is just a little algebra to keep things from getting really ugly. Okay, so I get negative y plus 1 on the top. And on the bottom, I'm going to rearrange a little negative pi y sine pi y. Okay, so 0 over 0 still. I'm going to apply another L'Hopital's rule. Limit as y approaches 1. The derivative of the top is a negative 1. The bottom is going to need a product rule. So I'm going to take the sine pi y and multiply it by the derivative of minus pi y, which is minus pi. And then I'm going to take the minus pi y, so I'll leave it minus, and multiply by the derivative of sine pi y, which is cosine pi y, times another pi, which I'll just make that a pi squared. Okay, so the top is now definitely not 0. Let's see what we get in the bottom. The sine of pi is 0. We're over on that left-hand side. Y value is 0. The cosine is negative 1. Okay, so this first chunk is gone, but then we get negative pi squared times 1 times negative 1, which means, oops, where are we? The value of our limit is negative 1 over pi squared. So messy, but still just applying L'Hopital's rule until you get something that's not indeterminate. Okay, last but not least, as theta goes to 0, we're getting 1, and then 1 over a tiny number, so we're getting a 1 to the infinity, so this is going to be another natural log. So the limit as theta approaches 0 of the natural log of the cosine of theta to the 1 over theta squared. Lots of parentheses. Okay, so I'm not immediately answering the original question. I'm posing myself a new, easier question, and I'm going to use it to help me figure out the answer. So limit as theta approaches 0, and then the natural log allows me to bring this out, make it a 1 over theta squared. In fact, I think I'll just make it a fraction. So I'm going to have the natural log, whoa, hold on. Those limits and natural logs are messing me up. Of the cosine of theta, and I'm multiplying by 1 over theta squared, which is the same as dividing by theta squared. Now, as theta goes to 0, cosine of 0 is 1, natural log of 1 is 0. I finally have a 0 over 0. And I can apply a L'Hopital's rule, and I get the limit as theta goes to 0. Derivative of natural log of cosine theta is going to be a 1 over cosine theta times a minus sine theta. And then on the bottom, I'm going to have a 2 theta. This is still looking like a 0 over 0. The bottom's definitely 0. And in the top, the sine of 0 is 0. So I think we just want to continue, but I'm going to rewrite a little first. I'm inclined to say I'd rather have a single trig function than a fraction in the top. So sine over cosine is the same as tangent, and that minus will just hang out. And then we can apply our L'Hopital's rule again. And we can say derivative of tangent is secant squared. And derivative of 2 theta is 2. We're interested in what happens as theta goes to 0. So remember, secant squared is 1 over cosine squared. And if we plug in 0, cosine of 0 is 1. So we're really just getting 1. Secant squared is equal to 1. So negative 1, which means our answer is negative 1/2. But that's an answer to the question, what happens to the natural log of the cosine of theta to the 1 over theta squared? So we know that that goes to negative 1/2. The real question was, what happens to cosine of theta to the 1 over theta squared? Which means we need to exponentiate with that base of e and say that our answer for the cosine of theta to the 1 over theta squared is that that'll approach e to the negative 1/2. Okay, so lots of examples. Hope that gives you some good ideas. Always let me know if you have questions.